All right, next up we've got David Adan. Welcome, David.
Thank you. Thank you. Nice to be here.
So give us a little background on yourself and your experience with Houdini.
Sure. Well, I started with computer graphics early on. I got hooked with computers and graphic programs since high school. And after that, I started using professionally some 3D software. So I started as a generalist, doing mainly television work, a lot of illustration, and some multimedia. And since I lived in a small city in Mexico, there wasn't that much production, especially television, which I really liked. So I started getting architectural visualization work because there was a huge architecture boom. So a lot of construction, hotels, restaurants. And I did a lot of visualization. And I continued with that for almost 6 years. And after a while, I really wanted to go back to production, and especially VFX. I really liked film. I think deep down, I really knew I wanted to do VFX for film. So I started working on that route again. And at some point, I started hearing a lot about Houdini, and there was a huge buzz. And I just downloaded the educational version, and I really liked it. I started studying. It was kind of difficult at first, but after that, it was just really fun and really flexible, I think. I really liked that. And I was also doing a lot of freelance work. So it really helped me to have everything in one single package and start doing small stuff, television, local stuff, some national television. And eventually, I got into a big studio in Mexico City, all in VFX. And I think my first film there was Jumanji, Welcome to the Jungle. So I started using Houdini for VFX, and it's been Houdini all for me from that day. So I really loved it. Currently it's my main tool.
Excellent. So what's your presentation going to be about?
So the presentation will be about natural destruction. So initially I thought about destruction because Houdini is I think it's known for the rigid body dynamics and volume and all that stuff. But then I kind of realized it was not only about destroying things, but also creating things for destruction, and how destroying things makes your creativity like live and go. So I will also talk about creating stuff procedurally and some workflows to really use the strengths of Houdini to go through the entire pipeline.
The thing I find interesting about destruction is that you need to understand the physics. You need to understand the construction of materials in order to destroy them well.
Correct. And that's an interesting part because every time that I'm going into a scene, it may be simple or complex, I go first through the process of how this thing would be created and how would it bend, how would it crack, would it just shatter. And this initial creation process and creative process helps me a lot to create the destruction.
Excellent. Well, looking forward to it. Let's jump in.
Okay, thank you very much and hope you enjoy it. Hello, and thank you very much for being here with me in this presentation, Natural Destruction in Houdini. First of all, I'd like to say a huge thanks to Alan McKay, whom I consider my mentor and friend, and probably I wouldn't be here without his help and all his teachings. I would also like to say thank you to Saber Gilasi, whom I consider my Houdini mentor. And also huge thanks to Alexandre Aile, who is my head of department and who usually gets me out of trouble when VEX coding gets very tough or when I get stuck with any gaffer or pipeline situations. So that being said, let's get started. First of all, I'd like to present myself. Usually when I speak to someone in the VFX industry, I'm very curious about how they got there, how they learned, or in general, know a little bit of their background. So me, I started as a 3D generalist, mainly doing local television commercials. I was always passionate about 3D and animation, so I started learning by myself. And professionally, I did a lot of multimedia, a lot of illustration. Eventually, I got into architecture because I lived in a small city in Mexico, and really television work was not that much. So there was a lot of architecture going on, and I had the chance to do a lot of visualization for restaurants, for hotels, and I started to get noticed in this industry. So eventually I got the chance to travel to Qatar, where I worked for almost 6 years doing visualization. But I think that since I started learning 3D, deep down I always hoped to get into the film industry. So I started to look for jobs specifically in the industry, and had the chance to find work as a compositing artist in a small studio in Mexico City called Flipbook Studio, where I did mainly work for national television, a few Netflix shows, and I started practicing Houdini a lot. I really loved the package, and I really liked the flexibility and the possibilities that it opened to me. So I started studying a lot, and eventually I had the chance to work in Olin VFX, which is a very big studio in Mexico City. And there I started again as a comp artist, but eventually made my way working with effects. And nowadays, Houdini is my main tool, and I'm doing full-time for films and television. So currently I'm working in Cinesite Montreal as a lead effects TD, and mainly, of course, working in films, some television shows. And some of the projects I've been involved in since I've started working in films are Godzilla, King of Monsters, Jumanji, Welcome to the Jungle, Terminator, Dark Fate, Angel Has Fallen, Asura, American Gods, Lost in Space, and a few other Netflix shows. So let's get started with the presentation. So here are the topics we're going to be speaking of today. First of all, I'm going to talk about the problem-solving approach, and this is something very personal. This is how I try to think in order to solve a problem, specifically a VFX problem. We will also talk about procedural modeling tools and how HDA creation can help you a lot in streamlining your workflow. We will also talk about generating asset variations with top networks. This is very useful, especially when you're creating a huge amount of assets. In the way, I will talk about some very useful hidden gems that sometimes we just lose sight of. And the meat of the presentation will be centered on different techniques for simulating natural destruction, specifically volume, procedural animation, wire solver, bullet solver. And these are not all the techniques that can be used. They are just the ones that I explored in some specific projects. I'll talk about them in a moment. And lastly, we'll talk about handling large amounts of data, that this is a very common thing when working with nature. So in general, trees, bushes, grass, flowers, all these natural phenomena really require a lot of data to be generated and handled. So real quick, why I chose this topic. First of all, nature is very beautiful, of course, but it's one of the most complex things to simulate and to replicate. And it's not very common to see tutorials or information about this. And still, it's a common thing that we get in production. So we usually have in a set extension some kind of tree or a bush, or at some points interaction with this kind of objects. And I think it's very important to have this kind of knowledge in your arsenal. So one of the very interesting projects I was involved in a few years ago was Godzilla, King of Monsters, where Olin VFX was in charge of creating a few time lapses of natural growing through decaying cities. And this involved a huge amount of nature, trees, plants growing, buildings collapsing with all this vegetation. And we had a very small amount of time. So we had to find a way to very quickly not only create all these assets, but then destroy them in a convincing way. And initially we thought that this being a time lapse, the animation wouldn't be that complex, but I think it turned out to be the other way around. Since we had to convey a huge amount of years going by, we needed to create plants that grew, that died, that withered, and all this happening very quickly. So all these elements had to be present, even if you weren't able to pick them up in a very obvious way. So let me show you the final result and the breakdown of the shot. This specific shot is in Las Vegas. And then we will move on with the technical stuff, and I'll be diving into Houdini to show you some very similar setups. So there you could see some of the trees growing, the vines creeping onto the buildings, the vines collapsing with the buildings themselves. Some of the trees die, some are growing, then bending or withering. So it was a quite complex scene. And overall, I think we did a great job, not only because of the very small amount of time we had, but also the result we really liked, and it was a very fun project to be in. So a huge shout out to the Olin VFX team, very talented and very experienced team. So real quick, before we dive into Houdini, I will talk about my personal problem-solving approach. And again, this is something that I try to do in every single project. You may find different ways of doing it, but I'll try to quickly explain my approach. So first of all, I analyze what we want to achieve. And this may seem a bit obvious, but sometimes we overlook certain details, especially with nature. So I usually start with the generic problem and then try to break it down into smaller pieces. So let's say we want to break a tree, probably have it bend, then break, and then crash into the ground. So that would be the more general task, but I would also start to think in more specific problems. For example, if the branches are bending, if the leaves are detaching, or if they have their own specific movement. And then I would start to gather reference. For example, if I need to break a specific tree, or if I need to animate it in a specific way. So the more reference you can gather, the better. And it can be pictures, it can be videos. So now I'm going to show you a few videos that I gathered for bending trees, falling trees. This is more specific for larger objects. This is a very good reference for the bending of the branches, all the leaves flying, the debris, the branches smashing onto the ground. Another very nice reference of the trees bending with the wind. All the leaves again, all the debris, that giant tree falling to the ground. So all this reference is very important and very useful for us. So once we've gathered all this reference and we've analyzed the problem, what I usually do is try to take into consideration how much time I'm going to have to create this effect and how much detail I will be able to put into the animation or the effect. And this is a very simplistic way to portray it. But in every single project that you will be involved in, you will have to balance and to play with how much time you can put into the effects. So next, I would try to identify every possible obstacle that could arise, be it lack of software, lack of knowledge in a certain aspect of the software, probably time constraints or budget constraints. So the earlier you can identify all these obstacles, the earlier you can address them. Next comes R&D, and this is very important and a very essential part of the process. So usually here I would start to think, okay, what technique I can use to probably make the breaking or the bending, and I start trying different possibilities. So I would try a volume solver and see how that looks. Then probably try a wire solver and compare both results, then go into rigid bodies, etc., etc. Then the implementation. So once I've decided what route to take, work in the implementation of the effects to full detail. And lastly comes iteration. And especially when you're doing simulations, it's very important to have time to iterate and to try different settings. And the more iterations you have, the better the effect will look. Okay, so now let's dive into Houdini. So first of all, I will show you a few procedural modeling tools that I've created. I will also explain how to generate several variations of models very quickly using TOPS networks. And I will also explain how to handle external 3D models, in this case, speed tree models or probably trees from libraries that you have bought or that you acquired. So even before you start destroying, you need to create something. And it is very important, this process of thinking how I'm going to break this object or how I'm going to destroy it. And in this sense, how I'm going to build it. So Houdini, I think, excels in creating procedural geometry, and especially geometry that will be prepared for this destruction or the following simulations. And of course, you can always use existing 3D geometry, but the better you prepare this geometry, the faster you will be able to create or to dive into your simulations, and the better the results will be. So I'm going to show you this asset that I created, and it's a simple tree creator. So normally I would start by creating the trunk of the tree and then think of the shape by adding branches. So here I can add secondary branches or level 2, level 3 branches. And then I can go beyond that by adding more detail. And on each branch level, I can create twigs. And on these twigs, I can create leaves. So the advantage of creating the own asset is that, first of all, you can animate all these parameters. Also, the geometry will be very well suited. In this case, it is watertight. I can change the level of detail. So I'll turn off a few of these elements. So of course I can add materials. I can change colors here just for the viewports, or even these colors can help me with the materials. Say for example, the leaves can have a gradient and have the material inherit this color. And here I can easily change every single aspect. Of course, the height, the number of branches. And this is something that you will usually never have in pre-built models. So, of course, they may have an extreme amount of detail and textures, but you will have only one tree and it probably comes with a huge amount of polys and you're stuck with that. You need to work with what you have. And here you can very easily change and art direct every single aspect of the tree. I also have a twig creator. So this is a seemingly simple tool. It's based on the L system. I think L systems are one of those overlooked tools that it can be very useful. So I can start with a specific tree or twig type. And then build from there. And a very nice feature of the L system is that it can be easily animated. For example, I can change the generations and I will have more and more complex and more detailed objects. Of course, I could also change other aspects of the shape. For example, the radius, the level of subdivisions. And I could also add additional noise. And as you can see, the possibilities are limitless. So once you have your tool, you can really play and art direct all these aspects. And it seems that you will have to invest a lot of time in the tool, but once the tool is there, you can change it and you can use it again and again in different projects and in different situations. So once you have your tool, you can pack it into an HDA and publish it for other artists to use. Now I'm going to show you a very powerful way of creating variations. So usually if you're doing a forest, if you're doing a jungle, any type of environment will have a huge amount of different assets. So even if you have one single type of tree in a garden or in a forest, you will want different shapes for that tree. And this is where top networks comes in very handy. So here I have my asset again. So as you saw earlier, I could change the shape, the amount of branches, how they bend, how they twist. And what I have done here to the right is I have created a top network. So I will dive into the top network. And in here, I created a wedge node. So what the wedge node does is it will create an attribute. And this attribute can have several values. In this case, I'm using values from 5 to 10. And this parameter here, wedge count, will define how many variations of this range will be created. So let me cook this node. I can Shift V to cook or process this node. And you will notice now we have these 3 dots. And if I click on each of these dots, I will get a different result. So what is this attribute changing? I will go back to my asset here. And here under the trunk, I have a parameter called bend. And notice here I have the name of this attribute, wedge bend. So this value, the angle, will be replaced with the values that are being generated with this wedge. So let me show you. I'll disconnect it for a moment and change this angle. So this is what I'm doing with the wedge. So I will undo to get back to my attribute. And again, dive into the top net. And here you can clearly see each time that a variation of the tree is generated, the bend goes from 5 to 20. And since I'm using a value of 3, the result will be a tree with an angle of 5, then a tree with an angle of 10 degrees, and finally a tree with an angle of 20 degrees. So after that, I am wedging a noise offset. So let me cook this node again, Shift V to cook. So now I have my 3 variations of the noise. Then each variation will have a variation in bend. So this will yield 9 different trees. So as you can see, this can very fast and it can very easily grow exponentially. Again, I'm creating a wedge just below that will change the position of each branch. So let me cook this one too. And now I will have a huge amount of variations, 27 to be exact. And each one will have different positions of the branches, different bending, different noise. Finally, I am caching all these results. So this node is similar to the sub-level rough geometry node. It will cache everything that's being processed upstream. And then I can read those caches here with a single read file. So I added this attribute just to quickly go between all these generated trees. And probably you can decide that you don't like one of these versions and you can delete it and recache and change your wedging parameters. So as you can see, the possibilities will start to grow, and you can real quick generate a huge amount of variations. So in this case, we will have 27 or let me see. Yeah, 27 variations of trees. And of course, you could spawn different variations for different kinds of trees. And this can be very powerful. Finally, I will show you how I handled speed tree models. And of course, many times you will want this very detailed kind of models. And here I'm just bringing in the tree. I'm separating the trunk from the rest of the elements. So here I have the twigs, and then I separated the leaves. And mainly the things that you want to be aware of is whether the geometry is closed. For example, make sure that you cap the ends of the trunks. And also, probably you may need to change the poly count, probably optimize the leaves, or probably bring down the poly count on the branches or twigs. But in general, once you have the model ready, the treatment for the animation and the simulation will be similar or practically the same. So regarding the actual simulation for destruction, again, Houdini has a huge amount of tools. And one thing that I really like about the software is that every single artist will have a different approach to the problem. And you can choose to use a procedural method or probably a volume solver or a while solver. Each one will have its pros and its cons. And as long as the result is what you're looking for and it's conveying your idea, it doesn't really matter what technique you use. But what I usually try to do is go from simple to complex. So let's say we have an animation of a tree and you don't need that much detail. I would try to resolve it procedurally or with modifiers that are there just created and at hand. And only if I need much detail, I would go into simulation or more complex solutions. So I will show you an example where I used a combination of procedural animation and wire solvers to create a convincing bamboo grove. So again, here is our bamboo model. And what I usually try to do is separate each task. For example, create an overall animation or simulation, and then generate a secondary simulation for other details. So let's start with the trunk. In this case, I only wanted a very simple swaying of the trunk. So I added a bend and created a very subtle animation using a sine function. So all I had to do is create a simple expression here. And as long as I play the animation, the tree would be bending from left to right. So that is very straightforward and very effective. Now, regarding the twigs, I separated the elements. Here I merged them with a few other twigs that were separated from the trunk. And then here I'm creating a very simple skeleton made with lines. Then replicating the bend that we had in the tree, in the trunk. So it was as simple as copying and pasting this modifier. And then I'm feeding this very simple animation to a wire solver. So if I dive into the DOP network, you will notice that the actual simulation is very simple. I am only attaching this first point of the twig to the motion of the trunk. And here with a wire solver and some simple gravity, I'm having these twigs sway and bounce with the gravity and the air. So you could add noise, you could add turbulence, some wind. In this case, I wanted something very subtle, so I decided to turn off all additional forces, and only the swaying and the gravity are doing the rest. So here I'm caching the result of this simulation. I added some color just to clearly differentiate the twigs from the trunk. And regarding the leaves, again here I'm isolating the tree's element, the leaves. What I'm doing here is on each leaf, I'm creating a gradient that goes from black to white. And this will help me to add some noise and multiply this noise by the color of each point. So again, this will be procedural animation. I'm creating a rest position, and all these leaves will follow the animation of the twigs with a point deform. So very simple solution. This has no simulation. I'm only using the animation that's been cached to drive with this point deformer the rest of the geometry. And here I'm adding the noise. So again, a very simple expression driven by time that's changing the offset of the noise. So I will increase the amplitude so that way we can appreciate this more clearly. So this will yield a much more complex animation, and still I'm using very simple tools. And notice how everything is processing very fast. And in the end, with all the elements combined, we'll have a finished animation. Okay, so what I did next was I generated a Redshift proxy. And this is just because I was rendering with Redshift. But if you're rendering with Mantra, you can always pack the object and the result would be the same. This will let us instance this object a huge amount of times without having a huge impact on memory. So let me turn this individual tree off. And here I have an instancer. And I'm instancing, I don't know, it's a huge amount of trees. Let me see how many trees we have. So here I have 800 trees. But what I did afterwards is I created 3 different variations of the bamboo and instanced each variation another 800 times. So here we have roughly 2,500 or so trees. And since we're instancing a proxy, even in the viewport, we will be able to handle this information. So let me look through the camera. And I'll show you a quick flipbook that I generated. So one thing I really like about the instancer is that although you're seeing most of the bounding boxes, you can also see a few of these instances. And this gives you a very clear idea of the proportion of the trees, how they're moving, the speed of that animation. So again, we're handling a huge amount of trees in this shot, and I will show you the final result. So this is the final render. And again, in this case, the animation is very subtle, but it's enough to give life to the trees and make it much more natural. Next, I'm going to show you how this dandelion was animated with Volume Solver. So first we have a very simple wind, making the flower bend and sway. And then the wind is increased and all the individual seeds are breaking off and flying through the air. And one thing I really like about the volume solver is it's usually very fast to set up, and it's also very fast processing a lot of objects. And in this case, we have a very natural bending and flying of the individual seeds. So let's take a look at the scene. As you imagine, the scene is not very complex. So this is the geometry. Everything was modeled within Houdini. So this is the stem. To create the animation, I added a simple line. I bend it just to follow the shape of the geometry. Then I pinned the bottom point, added some volume hair constraints, and then feed that to a volume solver. And this is just adding wind, super simple setup, but it will give me a very nice bending and very nice motion of the stem. So below I'm caching this animation. So with the result of this line, I'm point deforming the geometry. Then I'm caching this animation. So there's the base. Now I'm generating some areas where I'm going to scatter the seeds. Here I'm copying the individual elements and again feeding this into a volume constraint and a volume solver. Again, I cached the result of the simulation. And this is a different approach. What I decided is to simulate only the lines, and afterwards I'm generating the model of each of the seeds. So I'm creating a for each loop that is generating the geometry. So let me show you with a single iteration just to make this faster. So here I have the simulated line from the volume solver. Then I'm creating some depth or some thickness with a polywire. I'm extruding some pieces, adding a subdivide, and then looping through every single element. And this is creating the entire geometry. So finally, what I did is merge both geometries together to have the final result for rendering. So I really liked this approach because it gave me the flexibility to handle only simple lines, very quickly have some feedback on the animation, and then worry about the colors, the actual geometry, the shape of the seeds. And this made it easy for me to generate a huge amount of iterations and very quickly decide what I liked the most. So finally, I want to talk about rigid body dynamics. And in my opinion, the bullet solver is one of the most powerful tools to create destruction. And even if it's organic and natural destruction as this, where the bullet solver would seem somehow awkward or probably wouldn't be your first choice, one thing that I really like about the solver is it can handle a huge amount of objects, and it's very flexible in terms of how you want to control specific aspects of the simulation. For example, you can create different groups of constraints and change the flexibility of each constraint. You can make the constraints break with more or less strength in different areas of the geometry. And I personally really like the solver, and I'm very comfortable using it. So for this type of natural destruction, soft constraints can be very useful and can be very convincing in the way how the geometry moves and reacts to forces. So let me show you real quick what I want to achieve. So this is our detailed model, and I'm adding some wind. Again, it's a wind that's increasing every time, and eventually the trunk will break and it will snap, but I wanted it to bend. So if you remember the references, they slowly fall down. It's not like a very impactful thing. First, the wood will break and splinter, and then it can slowly fall down and bounce. So I want to feel that flexibility of the branches and that kind of slow reaction to the forces. So let's see how this scene was built. Again, I'm starting here with a tree generator, and I'm separating two elements. Again, the trunk and the branches. And first of all, I want to show you how I'm splintering the wood. So this is a very nice trick. I'm transforming the tree. I'm shrinking it down. Then I'm scattering some points exactly where I want the tree to splinter. And this will also help me define an area where the constraints will break. Then I create the typical Voronoi node, and I'm inverting back the transforms of this node. So I'm copying this value, the scale, and channel referencing to this other transform. And here's a hidden option, invert transformation. So really you don't need to do the math. You just click on this option and you'll have your tree back to its original scale. Now, what this will do is will create a very nice splinter look. So here you notice it's not just your simple cell shape. This is much more organic. And then I will feed this into the constraints. So first I will merge it with the branches and create the constraints for my rigid body dynamic simulation. So everything fairly standard here. I'm creating a rest position for the geometry. I'm packing the pieces or the fragments. And then I'm creating a group called inactive. I'm selecting the lower points of the geometry and setting the active attribute to 1 for every single point in the geometry, and then converting this value to 0 to the inactive group that I created up here. So what this will do is will prevent the lower part of the tree to be blown with the wind or pushed away with collision geometry, and just allow the upper part to bend or break. So here to the right, as I mentioned, I'm creating the constraints. Then I'm creating a group of the constraints that will be breakable. The rest of the constraints won't be able to break. I'm setting some stiffness parameters. And then I'm feeding these two objects, the fragments and the constraints, to the top network. So let's dive into the network. So pretty standard stuff here. I have a turbulent force just to make the tree sway a bit. Then this animated wind to push it back and forth. A drag force. And down here, all the magic is happening. I'm creating a constraint network. And I'm attaching a bullet soft constraint relationship. So this is a soft constraint that will allow the tree to bend. So usually a hard constraint won't have this bending look to it. It will just break when it reaches the break point. But the soft constraints will somehow allow some play and some motion and will look much more natural. So here to the right, I'm adding a subsolver that is telling the constraint, it's generating a limit of force that the constraint can handle. So once the torque is over 1500, the constraint will break and surely the tree will fall. So let's take a look at the cached simulation. And you'll notice how we have this individual motion on the branches. Of course, we have the bending of the tree. And all this is due to this soft constraints. It's looking very nice. So now let's put all this knowledge in a much more complex simulation. So what I will do is scatter a bunch of these trees. So remember I showed you we cached a few trees. I will open that scene. So here I have my caches, all the different variations that were generated in the top network. And then I'm scattering all these variations into a very simple forest. So here I have a grid. I scattered a few points and copy the 27 variations of trees. So every single tree on the forest will be different. So that's very cool. And then as usual, I will separate the trunk from the branches. And as we did earlier, I will fragment the trunks with this Voronoi fracture, scale them back up, and here with the exploded view, we can check the result. So I usually like to add this exploded view just to have a clear idea of how the fragments are. Here, of course, for demoing purposes, I don't have that much pieces, but the more pieces you have, the more flexible the tree can be. Again, I'm merging back in the branches and twigs. So I'm separating them because the twigs don't really need to be fragmented. That would be overkill. And then again, I'm generating the constraints, just as the previous example I showed you. Again, creating my inactive groups and feeding this into my DOP network. So here the only difference is I'm adding a collider. So I created this ramp just for testing and debugging purposes. And I created a huge amount of logs that are falling and will collide with the trees. The rest is the exact same setup that we already saw. So here I have my constraint network. Here I have my soft constraints and my subsolver to break the constraints. So here is my point wrangler with a very simple VEX code that will make the constraint break if the torque goes beyond this value. So let's take a look at a cached simulation. This is a result. So we have this falling collision object. And these are very heavy objects. They have a greater mass than the actual trees. And as soon as they start hitting the trees, some of them will break. Some will only bend if the force is not high enough. And here you can ignore this very slippery motion. I did this so that all the pieces reached the entire forest. And here is where iteration becomes very important. So at this point, you will usually want to test the different values. For example, the stiffness of the constraints, the amount of force or the mass that each object has, the strength or the amount of strength of the individual forces like wind, turbulence. And again, as I mentioned before, the more iterations you can create, the better the effect will be. Each iteration will usually yield a better result. Okay, so now let's see what happens with the rest of the elements. So here what I'm doing is, again, I'm isolating the twigs. Of course, this is already cached. Remember I mentioned I usually try to generate a primary simulation and then generate secondary simulations of smaller elements. So once we have the trunk and branches animated, I will generate the leaves. And what I did here is, since I was going to have thousands of leaves, probably even millions of leaves, what I'm doing is I'm generating a cluster of trees. And I'll speak a little bit more about this when talking about handling the data. But the goal here is for me to very quickly iterate, see some results, and also be able to cache a huge amount of data by separating the elements. So I'm scattering some points here. Everything pretty standard, changing the p-scale value of the points, adding some color. So here's a gradient. Jittering the position of these points a bit, and then copying the actual leaves to these points. Now here I'm generating a rest position, and this part is important. The reason I'm doing this is I will point the form, the leaves, with the animated twigs. So here to the left, I have the animation of these individual twigs. And this geometry will point the form, the leaves. So basically, it will inherit the motion into these scattered objects. And the reason I created a rest position is, remember I added some animated noise to the bamboo leaves. So I'm doing the same thing here. I want this secondary animation, this secondary motion, even if it's subtle, with this noise, I'm able to animate the individual leaves. And of course, I could also create a volume simulation. And this is where this balance between time, budget, and amount of detail that we want to put into the effect will come into play. So right now I opted for a very simple solution, just adding some noise. And this will add to the point deformation to create a very convincing and very fast effect. So let's see how this flipbook looks. So it's the same animation that we already saw. We have the falling trunks colliding with the trees. And to the right, we can see the animation of the leaves. And what I would do in a more complex scene, for example, here we have 27 trees, which is quite a lot, but a typical forest or jungle would have hundreds of trees. So I could cache separate clusters of leaves and make it much more manageable. And of course, right now, I'm generating this iteration very fast. I can debug the leaves with just a single or just a few elements and then extrapolate this result to the rest of the trees. So in the end, what I'm doing is bringing in the entire forest. Of course, we could blast whatever element we don't need, and merging the rest of the elements. In this case, I'm merging the twigs. And then I'm merging in the leaves to have the final result. And remember, I mentioned that the bullet solver can handle a huge amount of data and a huge amount of objects. And this simulation, if you notice, I'll go back to the cached result. This simulation is calculating the trees, the branches, and the twigs. So here we have several thousand pieces. And I think I could easily add 5 or even 10 times the amount of trees that I currently have. So let's take a look at the simulation from another angle. So this is seen from the left view. And again, all these flipbooks that you can generate will help you evaluate the look and iterate when necessary. And of course, not always things go as expected. So sometimes we have some very happy accidents. In this case, we have a very nice reaction to these constraints. So here what happened is I forgot to create a rest length value for the constraints, and I had this very weird and yet funny result. And this is all part of this R&D process. And it's also learning, because probably it's not working for this particular case, but maybe it will be used in some other situations, or it will at least show you something that you didn't know or that you forgot. Or sometimes you need to research and find why these things are happening this way, or why the results are not as expected. And here we have a very funny example. So this was a volume. It was one of my first attempts of creating a volume simulation. And at some point I kind of gave up, and I thought, okay, let's go back to a very simple procedural animation and the wire constraints. Okay, so as I mentioned earlier, usually when you're creating these natural scenes, you will be handling a huge amount of data. So being it geometry, for example, leaves, branches, twigs, or cached points, probably cached simulations. So whatever you're doing, you'll end up with gigs of information. And the way you handle this information can make it easier or faster to work. So here are just a few pointers that I've been using in recent projects and things that have worked for me. So first of all, scattering packed instances or proxies in case of Redshift or probably Arnold, you can decrease the memory footprint of your scene and make it more optimized for you to preview on the viewports and even render. So you could render literally thousands of trees using proxies. So remember, my bamboo grove has almost 3,000 trees and the renderer is handling pretty fine. Another thing is clustering. So say, for example, you have a huge amount of geometry. Try caching these individual clusters in different packages, in different files, and then probably merging together or even rendering separately. For example, say you have different portions of a jungle or a forest, and probably the trees are separated between them, or probably they're not interacting between each other. You could render clusters separately, or probably render depending on the distance from the camera or whatnot. So in the end, the goal would be that all these techniques will help you manage more easily your scenes and your data. Okay, so as a brief recap, let's take a look of what we've seen so far, and hopefully you've learned a few new techniques. So I spoke about my personal approach to problem solving, and this is very useful for me because it lets me trace a roadmap of what I'm going to do for each project. Then we talked about some procedural modeling techniques and how we can create HDAs for these tools. And this way we can reuse them in several projects or for several cases. This makes it very convenient to reuse data. We also learned a very powerful way of generating several instances using top networks. Hopefully along the way you were able to find some new hidden gems. For example, the L system, which in my opinion is an underrated tool. I think that probably if you take the time to explore these tools, you'll find out that they can be very powerful and they can help in certain situations. We also took a look at animating and simulating natural phenomena. For example, the volume solver to break apart the dandelion seeds. Some very simple procedural animation techniques with the bend modifier and a few simple expressions. And we also added some very simple noise animation through the point wranglers and point vops. We also created some animation for the bamboo branches with the wire solver. And finally, we created a very complex destruction scene with the bullet solver. Lastly, we reviewed some tips to handle the large amounts of data that are generated with these types of scenes. So before I say goodbye, I want to leave you with some very useful links that I came across while doing my R&D. So first of all, tokeru.com, that has a huge amount of resources and a very nice volume forest example. Of course, the Entacma webpage has also a huge amount of very nice tutorials, and specifically a very nice tutorial talking about PDG and top networks. I also came across with a very clever and very cool tutorial from Fabricio Chamon to create this procedural skeleton for the wire solver. Also a very in-depth tutorial by Hossam Aldin called Tree Rigging for Feature Films. And finally, a link to the Mastering Destruction and Effects in Houdini from Rebelway, where they go in-depth with several destruction techniques and the soft constraints. So that would be all on my part. Hopefully you learned something new and you will be able to put all this knowledge into practice. I want to thank Side Effects for inviting me in this occasion to talk about Houdini. That is a wonderful tool, and to showcase all these techniques that I've been using in production. And hopefully we can meet again in the future. So thank you very much and goodbye.